Hi, I'm Paul. We are doing Leetcode must know interview questions. Today's challenge is edit distance. Given two strings, word 1 and word 2. Let me scoot this over so you can see the whole method signature. There it is. We've got a function called min distance. Input, word 1, word 2. All right. Return the minimum number of operations required to convert word 1 to word 2. There are three operations that we can use. Insert a character, delete a character, replace a character. So this is rated medium. I think it's a little bit harder than some of the medium ones that we've done just because we, at each decision point, there's three things that we can do. Not two, three. We can insert, we can delete, we can replace. Now, as far as recursion goes, there's still only two variables, and that would be the index of word 1 and word 2. There's two variables that change, so it's still a two-dimensional dynamic programming problem. But I think the fact that we have three options, it just gives us a little bit more to think about. Let's look at an example. Let's say we want to convert the word horse to R-O-S. How can we do that? One way to do it would be replace the H in horse with an R. And we get this, R-O-R-S-E. Then remove the second R. And then remove the E. And then we have R-O-S. How many operations is that? 3. Okay. Look at this. Let's look at this situation. We're going to start out with a recursive solution. We could do starting with a recursive solution is not a bad way to approach dynamic programming problems, because if you can come up with a recursive solution, you understand the recursive relations, then I should say the recurrence relations, then you can convert it to a top-down dynamic programming problem by memoizing the overlapping subproblems. Okay, a recursive solution is going to be very bad because it's an exponential algorithm, and in this case we get three choices, so it's going to be like a 3 to the m problem if we call the length of word 1, let's say m. Okay, yeah, actually let's start with that. Let's say we have m, and the length of this is going to be n. And actually, we can probably just go ahead and put in a line of, oh, you know what, I can't well, no, I think I can do that. We'll call it m and n, but actually I think what I want to do first is take the drawing. I was just going to put in the first line of code here. What we're going to do is we're just going to call a function here. We'll call it edit distance. Okay, we're going to pass in word 1. We'll pass in word 2. We'll pass in the length of word 1. We'll pass in the length of word 2. I'm going to scoot this over so it doesn't wrap. All right, and the length of word 2. All right, we haven't written edit distance yet, but what is going to be passed in there is, and let's give variable names to the length length. Let's call them M and N, all right? I want to try to explain this in a way so that we don't get confused about the length variables and the indexes, okay? Because at a distance, we're going to have to do comparisons using M minus 1 and N minus 1. Those are the biggest indexes that we can use for word 1 and word 2. So let's say that, well, there's a couple of possibilities. We're doing this, by the way, right to left. One character at a time, right to left. We could do it left to right. The ideas are the same, but we're going to go right to left. All right. Let's say that the rightmost characters in these words match. Okay. Well, in that case, we can call it again and just use M minus 1 and N minus 1. Right? That's a match. They don't match. Now we have three options. One, we can insert the last character of word 2, which would be word 2 at N minus 1, at the end of word 1. And then we call it again. We call it with M and N minus 1. Okay, here's another option. We can replace word 1. We can replace word 1 at M minus 1 with word 2 at N minus 1. And then call it again. That's a replace. If we do a replace, then we're really just calling it again from the same spot. M minus 1, N minus 1. And the final option is to do a delete. You can say they don't match. In that case, let's delete the last character of word 1. Now we're going to call it again with M minus 1 and N. Okay, so let's look at these again. So insert. Here's the original. The original comparison was M minus 1, N minus 1. If we do an insert, then word 2 doesn't change. Word 1 changes. So the next comparison that we're going to have to do is M and N minus 1. If we do a replace, then neither string changes in length. We just assume that we have made the match with a replacement and we move on to the next letter. All right. Final option, delete. Delete the character at the end of word 1. So word 2 doesn't change. Word 1, we are moving to the left, 1 index. All right. Base cases. Base cases are m equals 0, which means that string 1 is empty. In that case, the function would return n. It means string 1 is empty. String 2 is possibly not empty. So to convert an empty string to a string of size n is going to take n insertions. So if m equals 0, we're going to return n. Same thing if n equals 0, that means string 2 is empty. String 1 is possibly not empty, but to convert a string of size m to an empty string is going to require m deletions. All right. Good. So let's try and implement the rest of this. All right, so let's take a look at the recursive solution. Edit distance. So again, what we pass in here is the first string, the second string, and these are the lengths of the string. Okay, here's the two base cases. Again, if m equals 0, we're going to return n. If n equals 0, we're going to return m. If the characters that we are currently considering are equal. These, I mean, we start from the rightmost character in each string, and then we move to the left. But if the characters that we are currently considering are equal, then we make a recursive call to edit distance, and we decrement the indices by 1. Again, what comes in, these are lengths, not indexes. So we will decrement by 1. If they're not equal, we get 3 possibilities. One is an insert. If we do an insert, then we are still considering the last character of string word 1, but we're moving forward with word 2. All right, if we do a replace, then we can move forward on both characters. We assume we've done a replace. They're now equal. We'll move forward and we'll look at the next 2 characters. And the third option is to remove the last character from word 1, in which case we are still looking at the last character of word 2, but we are moving 1 index to the left in word 1. All right? And we're trying to find the minimum here. So recursively, this will compute all of the distances, but what we want in each case is the minimum of the insert, the remove, the replace. Which one gives us the minimum number of operations? And this is because, you know, for each time through here, for each operation, we have to add 1. Now, we can run this, and it's not going to work, I don't think. I mean, I think it's going to time out because of the recursion, but it gives us something to work with in converting it to a dynamic programming solution. So let's try, well, let's try running it first just to make sure that it compiles. What did I do there? Edit distance, word 1. Oh, I see. No semicolon. Okay. Missing return statement. Line 4. Oh. Sorry. Return edit distance. Okay. All right, that's accepted. Now we'll submit it and watch timeout. Time limit exceeded. The words were not even that long. I mean, they can get up to 500. So, okay, let's take a look at how to convert this to a dynamic programming solution. All right, so as I mentioned, the recursion, there are two variables that change during the recursion, m and n. And so the number of variables that change during the recursion determines the dimension of the dynamic programming table. So in that case, what it means is that we need a two-dimensional table of ints equals new int. Now the indices can go from 0 to m or 0 to n. So the table has to be big enough to accommodate that. And so we will do that. We need to initialize this table. So we can say for int ARR. I don't think I need to do that. Yeah, that is right. Because I'm switching back and forth. Where did that go? Switching back and forth between languages here. For int ARR in memo. Arrays fill ARR -1. So they'll all be -1. That means that we haven't processed that cell yet. All right. And then we need to pass it as part of the function call. And down here, we'll say memo. All right. What else needs to change? Oh, wait. No, I think that's all that needs to change up there. But down here, all right, the base cases are the same. Before we do any work here, though, we check the memoization array to say if memo m n is not equal to -1, that means we've already computed it. And we don't need to compute it again. Return memo m n. All right. If the characters are equal, let me copy this. The characters are equal. We are not just going to do a return. Again, we've got to memoize everything that we compute. So memo mn equals edit distance s1, s2, m1, s1, and then also the memo array. Okay. Else. Why is it over there? Oh, because I don't have a bracket here. Okay. Else. All right, we've got all of those. We well, okay, let me just copy this. No, you know what? I mean, yeah, let's just put it up here like this. Should I still copy the memo mn? Yes. Memo mn equals. What happened to my 1? 1, come on. 1 plus. And then the math min, insert, remove, replace. Okay. Close that and then return memo m n. Okay. Does that look good? Yeah. So that's how we change the recursive solution to a dynamic programming solution, is just to add the memoization table. Instead of computing things and returning them, we compute them and put them in the memoization table and then just do lookups. So let's try and run this again. Compile error, new int. Wait, what is that? Int memo equals new int. Oh, there is no m there. Sorry. You know what? There's a better way to do that. Just take that out. And then here we'll say int m equals word1 length, int n equals word2 length, and then down here we will send in m and n. Let's see if that works. Int insert equals edit distance. Method cannot be applied. Int insert. Come on. Int insert. Come on. I forgot to add the memos down here. Memo. All right, let's try it one more time. Accepted. Good. Now let's submit. Shouldn't be a time issue this time. There isn't. Okay, let's see what we got. That over a little bit. Here and here, and runtime. Runtime's quite good. So that is dynamic programming for edit distance. Again, you can do a recursive solution just to make sure that you understand the recurrence relations, add a memoization table that will convert it to a top-down dynamic programming problem. You can also do a bottom-up dynamic programming solution to this if you want to. In fact, that would probably be a good exercise. But I hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.